All right, thank you everyone for coming today to the Graphs and Matroids seminar. I'm excited to say that today we have Jakob Kneip talking about the fact that tangles are decided by weighted vertex sets.
Thank you, Rose, for having me. And what I'm about to present today is joint work with my two PhD colleagues, Christian Elbach and Maximilian Tegen, who together with me are doing the PhD in Hamburg. And as Rose said in the introduction, we're going to talk about the fact that tangles in graphs are decided by weighted vertex sets. And to start the talk, I will give you the key definitions for tangles first, and then show you the motivation behind these definitions and how tangles work intuitively. So, okay, that worked. Okay, great. So for the rest of the talk, G is going to be a graph, a finite graph. And the separation in a graph is a way to divide the vertices of the graph into two sets, which may and usually will overlap in such a way that there's no edge between the sets except for the overlap. So formally, we ask that there's no edge of G that has an endpoint both in A without B and in B without A. So if you want to get from this side of the separation to that side of the separation, you have to go through the separator here. Now, the size of the separator here, so the number of vertices in the intersection A cap B, is what we call the order of the separation. So if a separation has very low order, that means that in that place in the graph, it's very easy to cut the graph into two pieces by removing just the few vertices in the separator. Now, these separations are the key to tangles, the object of today's talk. So a tangle is a set of separations of order k, or of order less than k. So separations, as we've just seen, where you have fewer than k vertices in the separator. And we ask two things of the set of separations. The first is that for each separation of order less than k, our tangle contains either AB or the separation the other way around as B comma A. And whenever our tangle contains a separation AB, we think of this intuitively as the tangle saying that the B side, so the right-hand side of this pair, is big in the graph in some sense. And the other side is then small. So for each separation of order less than k, the tangle has to contain one of the two ways of orienting the separation, is to declare exactly one of the two sides as big. Now, the second thing that we ask of our tangle is that whenever you have three separations in your tangle, then their three small sides together do not cover the entire graph. So in other words, the big sides have to obey some sort of filter property here, which we phrase as that no three small sides may cover G. Now, the motivation behind these tangles is that whenever you have some sort of cluster or dense object in your graph, then really no matter which exact type of cluster that is, it's going to define one of these tangle objects here. So if you have a large cluster, think of your favorite kind of cluster maybe, then if this cluster is very large compared to this order k here, so separations cannot use many vertices to cut through the graph, then no separation is going to be able to cut your cluster into two halves. So whenever you have a cluster in your graph, it's going to be, for each low order separation, quite clearly on one side or the other. And this will define a tangle in the sense. And the second property in the tangle here, this is what we call the tangle property, that no three small sides cover the graph, is there to ensure that the tangles that you do get in a graph hopefully really do come from some substantial dense region in the graph. So let me illustrate that with two examples. The easiest type of cluster to have is that you have a large clique in your graph, or clique minor perhaps. And in that case, if you have a separation of low order, then clearly the entire clique is going to be either on the A side or on the B side. and declaring those sides as big is going to define a tangle in this sense. The other example is perhaps a bit more interesting. If you have a large grid in your graph, this grid has fairly high global connectivity, but each single vertex is not very well connected locally. So if you have a separation of low order, it might not be able to cut through the entire grid, but you can still maybe nibble a bit on the edges. So a low order separation is going to be able to cut off one of these corners perhaps, but still the great majority of the grid is going to be on one side. Or what you could try as well is to cut out a little ring in the middle of the grid, but again, the vast majority of the grid is going to be on one side of the separation. And if your grid is large enough compared to this parameter k, then the collection of all these separations, where you say that the big side is the one with the majority of the grid, is going to define a k-tangle. So in both of these examples, we had for our k-tangle, which in this case came from a cluster, we had a set of vertices which defines this tangle by majority vote, by which I mean that we had a set of vertices x, in this case either the vertices of the clique or the vertices of the grid, such that for each separation, the side that was big according to the tangle was precisely the side that contained the majority of the vertices in x. And the open question that we're interested in here is whether we can always find such a set x of vertices. So given any tangle in a graph, can we find a set of vertices such that the big side is the side with more vertices of that set? And the answer to that is we don't know. So phrased this way, we don't have a counterexample and we don't have a proof. What we can show is a fractional version of this. If you allow, instead of just having a set x of vertices, to have a weighting on the vertices, then this question has a clear answer and it's yes. So this is the result that I want to discuss today. So together with, as mentioned, Albert and Tegen, we showed that whenever you have a k-tangle in a graph, you can distribute weights on the vertices, non-negative weights, of course, in such a way that for each separation in your tangle, the side that's big according to the tangle is precisely the side with higher total weight. And well, what I want to show you today is the proof of this theorem and the ways to extend this to slightly different settings. So the proof of this theorem hinges on two structural observations about separations in graphs. The first of these, and what's written here is not the observation itself. For the first observation, we introduce a partial order on the separations of a graph. So if we have two separations A, B, and C, D, and the A side of AB is a subset of C, and the B side is a superset of D, then we say that AB is less than CD in this partial order. So if we think of these separations pointing to a cluster, then we think that CD is maybe a bit closer to the cluster, and that's the larger one on the partial order. Now, the observation is that if we have our tangle and we're looking for such a weight function that makes all the big sides of the separations those with higher weight, then we only need to concern ourselves with the separations that are maximal in this partial order. And you can see that in the picture. So if AB and CD are separations in our tangle, and we want to distribute weights on the vertices in such a way that the D side here has higher total weight than the entire C side, then if we can do that, we don't have to worry about AB. So the B side will have even higher weight than D, and A will have even smaller weights than C. So the first observation is, once with this partial order, only those separations that are maximal in this order are interesting for us. And the second observation now comes from looking only at these maximal separations and studying their relationship with each other. So say that AB and CD are two maximal separations in a k-tangle. And now if they're maximal, they're clearly not comparable themselves. So the picture is now slightly different. And let's look at the separators of these two. So red is the separator of AB and blue is the separator of CD. And you should be able to see the colors, I hope. Okay, great. So what we can now, what we can use the maximality of AB and CD for is to learn something about this top right corner in this diagram. So if we consider the separation where we take the union of the two small sides against the intersection of the two big sides, so A union C against B intersect D, then we will be able to say that the order of the separation cannot be less than k. So in other words, we will know that there are at least k vertices in the gray part here. And it's fairly easy to check that this expression here is indeed in separation. So any edge from the top right corner to somewhere else in the graph would have to go either through this separator or that separator. So this really is the separation in the graph. Now, why can the separation not be of order less than k? So if there are fewer than k vertices in the gray part, then our k-tangle would have to declare one of these two sides as big, either B intersect D or A union C. Now, if the tangle were to declare that B intersect D is big in this tangle, then we would contradict the maximality of A, B, and C, D, because this separation in our partial order is strictly bigger than both A, B, and C, D. So our tangle cannot declare this side as big. So again, if we have fewer than k vertices here, the only option left is that the tangle says that A union C is big. But this contradicts our definition of a tangle, because now B intersect D would be a small side, and so A is a small side, C is a small side, and together with this now small side B intersect D would have three small sides covering the entire graph. So it's not possible that we have fewer than k vertices in this gray bit. So there must be at least k. And now we can do a double counting argument. So the total number of vertices in the separators is certainly less than 2k. So there are at most k vertices here, there are at most k vertices there. Now, if there are k or more vertices in the gray part, then in particular, there are fewer than k vertices on the bottom left here. So in the two white parts and the middle. So what we learn from that is that these two, the red part and the orange part of these separators together contain strictly more vertices than the purple and the blue part at the bottom. So whenever we have two maximal separations, then those parts of the separators that lie on the respective big side of the other separation contain more vertices together than the sum of the vertices on the small sides. And this second observation is really the key to making the proof work. So what we're going to do is, instead of fiddling around with individual weights of vertices, we are going to assign a weight to each separator first. So for each of these maximal separations, we will assign a weight to that separator and then distribute those weights onto the vertices. So where each vertex will have as weight the sum of the weights of all the separators in which that vertex is contained. Now, this observation here tells us that if in this picture here, we were to distribute equal weights for the separators A, B, and C, D, then, well, we would not be guaranteed that for any particular of these two separations, that its big side would then have higher total weight than the small side. But taken together, the two big sides would have higher weight than the two small sides. So we would at least be right on average with that kind of weighting. So let's see how we can actually find a weight function this way. So as I said, we're going to assign weights to these separators first, and then turn that into the weighting of the vertices, simply by summing up for each vertex the weights of the separators in which the vertex lies. Now, the first thing we do is that we bring our problem of assigning weights to the separators in matrix form. And from there, we will then work with a matrix rather than work with the actual graph. So we take our maximal separations, A1 to some AM, and enumerate them. And now we define a matrix. So in our matrix, we will collect as the entry Mij. We will look at, let's call this the score of the separator of Aj, Bj with respect to this ith separation. So we'll be put into a matrix as Mij. For that, we're going to look at the separator of Aj, Bj, with purple and orange vertices here, and see how many of these vertices are on the big side of Ai, Bi, versus how many of them are on the small side. And the difference between these two values is our entry Mij. Now, the observation we've just seen tells us that if we sum up Mij and the flip of that, Mji, then we're going to get something positive. So we're not guaranteed that any particular entry Mij is positive, but any Mij together with its transpose value Mji is going to sum to something positive. Now, once you have this matrix, and we have chosen in some way some weights that we want to assign to the separators, how can we, from this matrix, calculate how well the weighting of these separators, or the weighting of the vertices we get from that, decides all of these separations? So say that we have a vector x in which we have encoded the weights that we want to distribute among the separators x1 to xm. And I'm now interested in the question whether for this ith separation Ai, Bi, I indeed have higher total weight on the B side than on the small side, the A side. So I want to compute the total weight of Bi minus the total weight of Ai. So, and we can see that that's going to be, so if xj is the weight that I've assigned to the separator here, I'm going to collect exactly Mij many instances of this weight xj in that sum. So if each of the vertices here gets the weight xj, then in total, orange many are going to contribute positively to the sum and the purple ones negatively, so I get Mij times xj. Now, if we look at this expression here, then we hopefully recognize that what we've written here is exactly the ith entry of the product m times x. So again, if we encode the weights of the separators in the vertex x, then the product m times x is going to tell us the total weight of the big sides minus the total weight of the small sides for each of our maximal separations. All right, so from now on, all we need is to find a vector x of weights that makes this product here have positive entries everywhere. So if we can find such a vector, then assigning those weights to the separators and then turning that into vertex weights is going to be exactly the weight function that we want. And doing that is a fairly routine application of the Forgash lemma from linear programming. So again, we're looking for a vector of weights, non-negative weights, that makes this product here positive, and I'm using these as coordinate-wise inequalities here. And we are going to use for this the second observation. So we know that in our matrix Mij plus Mji, this is red plus orange minus purple and blue, is always positive. So this means that for our matrix, we know that the matrix itself plus its own transpose will have positive entries almost everywhere. Not on the diagonal, there are 0, but every other entry is going to be positive. And here's the version of the Farkas lemma that we're going to use. So there are, well, many different ways of the Farkas lemma where you have lesser equal or bigger equal or strict inequalities or something. But today the Farkas lemma means exactly this. So given a matrix A and a vector B, the Farkas lemma says that exactly one of two things happens. Either we find a non-negative vector that makes this product AX, A times X, bigger than B, or there exists another non-negative vector Y such that the product with the transpose of this matrix is non-positive everywhere. And the second condition only really says that this vector is not simply 0. You were saying something, Rose? Okay. All right, so we are going to apply this Farkas lemma to our matrix M, and we'll use as the vector B on the right side simply the vector that has constant ones everywhere. So, well, there are exactly two cases that can happen. Either the first, so the first outcome of the Farkas lemma is that there is a non-negative vector such that the product M times X is coordinate-wise greater or equal to the constant 1 vector that we've chosen. So in particular, positive everywhere. So if this case happens, then we're done. That's exactly the vector that we wanted, and we have a weight function. The second thing that can happen is that we find another vector Y such that the product with a transpose of our matrix is non-positive everywhere. Well, in that case, we have to make use of our knowledge that M plus its own transpose has positive entries everywhere. So if this vector Y is non-negative, and this matrix M plus M transpose has only positive entries, then certainly their product is non-negative as well. So 0 is less than or equal coordinate-wise to M plus its own transpose times Y. But now, due to the nature of this vector Y here, that the transpose of M times Y is non-positive everywhere, in this sum, we can simply omit the M transpose part. So this is less than or equal the same expression, but without the M transpose. So the vector Y that we find here turns out to be almost the same as the vector X that we found here. So we get that M times Y is non-negative everywhere. So this is not positive everywhere, but if you then again look closely at the makeup of this matrix and see that this actually has positive entries everywhere, but on the diagonal, you very easily find that this vector Y indeed makes this product positive everywhere. So due to our second observation, which we used to know that M plus M transpose is positive, we find that with the Farkas lemma, both possible outcomes of the Farkas lemma give us the weight vector that we want. So with that, we have established the main result after, well, half the talk. So we have plenty of time to talk about possible extensions of this result. So let's quickly recap here. So we've shown that for each k-tangle in a graph, so each consistent way of declaring for each separation of order less than k, one of the two sides as the big side, we can find a weight function of the vertices that makes exactly the big side of each separation the side with higher total weight. Now, there are two possible ways of extending this result. The first of these is that we can think about the edges of our graph G. So far, the edges of G didn't really feature in any of the arguments that we were doing. So the separations we use have vertex separators. And the only time that we had any edges appear in any of the definitions was in the definition of the separation themselves, just so we have no edge from the left side of the separation to the right side. So we don't particularly care in this argument whether those were normal box standard edges or whether they were multi-edges or hyper edges or anything like that. So maybe not directed, but multi and hyper edges work just fine. So with the exact same proof that we've just seen, you can immediately extend this result to hypergraphs and multigraphs. The other way of maybe extending that result is if you don't want to use vertex separations. So if you study in clusters that are maybe defined more by edge connectivity than by vertex connectivity, then maybe these vertex separations don't capture those types of clusters very well. And in that case, you might be more inclined to study cuts of graphs. Maybe we can define tangles for cuts in graphs and get a similar result there. So here's how you would do that. So you can adapt the definition of a tangle almost without changes. So let's first define what a cut is. So a cut in a graph is a bipartition of the vertices. So this time we have no overlap between the two sets A and B. And the order of a cut is the number of cross edges. So edges that are incident with both A and with B. And for these, we can define a K edge tangle, again with this parameter K. So this is going to sound very familiar now. So a K edge tangle is a set of cuts of order less than K, which for each cut of order less than K declares one of the two sides as big. So it contains either A, B, or BA. And secondly, such that no three small sides together cover the vertex set. And now for these edge tangles, we do need a slight deviation. So we do need a third condition to make them interesting. We ask that for each cut in our tangle, the big side should be incident with at least K edges of our graph. Now, why do we need this weird third condition? So if we're now working with cuts rather than vertex separations, and if you have, say, a single isolated vertex in your graph, then this single isolated vertex would define a K edge tangle with the first two properties by saying for each cut of the graph that the side containing that one isolated vertex is the big side. Then all of the small sides here would miss that one vertex. So no union of small sides would ever cover the entire vertex set. But clearly, if you're looking for some sort of cluster, then isolated vertices in the graph aren't very interesting. So that's the reason we have to add this third condition to the definition. And with this definition of edge tangles in place, we can now more or less do the same proof again. So here's the result formulated for edge tangles. So we are, again, not really interested in whether the graph is a multi-graph or not. But the edges should be normal graph edges, so pairs of vertices now. And then we can find a function, a weight function on the vertices, such that for each cut in our edge tangle, the big side according to the tangle is the side with higher total weight in this weight function. And in fact, you don't have to change much for the proof. So if we, so you can define the partial order on these cuts in the same way as for the vertex separations. And again, you only have to care about the maximal cuts. So maximal cuts now meaning maximal in this partial order. And the same observation, so the second observation is true as well. So if you have two maximal cuts in your tangle, then you will, by the same type of argument, know that the total number of cross edges of this top right corner here, so all of these cross edges here, are going to be strictly, they're going to be strictly more cross edges here than on the bottom left corner. So you get the same inequality. You can write those into a matrix again and use the Fokker lemma. But this time, what's a bit different is that once you've chosen weights for these cuts, you have to be slightly careful when turning that into a weight function on the vertices. So previously, we had weights on these separators, which were themselves vertex sets. And it's pretty clear that if you have a weight for a separator, then each vertex would simply inherit that weight. Now, this time, if we've chosen a weight for the cut AB, then we want the end vertices of these edges to inherit this chosen weight for AB. So if we have, say, assigned weight 5 to AB, then each of these end vertices is going to obtain a weight of 5 from this cut. However, this vertex right here that's incident with 2 edges of this cut is going to receive this weight twice. So this is now the only real deviation from the proof before, that when defining the weight function on the vertices, you have to account for the multiplicity of edges appearing in these cuts. But with that, the argument works in exactly the same way. All right, so hypergraphs do work. Edge tangles do work. So what about edge tangles of hypergraphs? Now, interestingly, there the result fails. And to conclude this talk, I want to talk you through an example of that shows why this fails for edge tangles and hypergraphs. So let's define the example. So the hypergraph H that our counting example consists of uses as vertex set the 3-element subsets of the integers from 1 to 7. And don't worry, you'll get a picture in a moment. And we will use, it has 7 hyper edges. So for each integer from 1 to 7, we put all the 3-element subsets which contain that chosen integer into one hyper edge. So here's a picture to illustrate this. So V consists of all these triples of integers from 1 to 7, and the hyper edge E1 in this case contains all those 3-element subsets that have a 1 somewhere in them. And in this hypergraph, there's an edge tangle, which we can define the following way. So for each cut of order less than 7, so this means for each cut that misses one of these hyper edges, and once more, by the definition of these hyper edges, this means for each cut where there's some integer that appears only on the tuples of one of the 2 sides of that cut, we say that that is the big side. So once more, for each cut that misses one of those hyper edges, so where one of the hyper edges is either completely in A or completely in B, we say that the side containing that hyper edge is the big side of this cut. It's maybe not immediately obvious that you can't have hyper edges on different sides of this cut. But if you think about it, if you have a hyper edge on the right-hand side of this cut up here, so in this case, all tuples containing a 1 are on the top right, then while all tuples containing a 1 will contain all the integers from 1 to 7. So you can no longer collect for some other integer from 1 to 7 or the tuples of that integer on the other side. So this here really does define, well, it defines something where so we can, for each cut, define one of the 2 sides as big in the sense, and this is actually going to be an edge tangle. If we look at any 3 separations here, we will have 3 hyper edges on their respective big sides. So maybe EI, EJ, and EK. And then we know that the triple IJK will be on the big side of all three of those cuts. So the small sides of these separations cannot cover all of these three element subsets. So this really does define an edge tangle in a hypergraph. And now all we have to do is somehow prove, or at least convince ourselves, that we can't possibly define weights on the vertices here to make the big sides of these separations, the big sides of these cuts, the sides of higher total weight. So for that, in this edge tangle, I will tell you the maximal elements of this edge tangle. So the maximal separations are those where you pick one of these hyper edges. So you pick one of the integers from 1 to 7, and then the big side of your maximal cut will contain exactly those tuples which contain that chosen integer. So here, A1, B1 as the big side, B1, all the tuples containing a 1, and everything else on the small side. And with that, we can consider this expression down here, where for each of these 7 maximal separations of our edge tangle, we take the total weight of the big side minus the total weight of the small side. Now, if our weight function indeed has the property that for each separation, for each cut in the tangle, the big side will have higher total weight, then this is clearly a positive sum. So each of the summands here, each of these differences between the big side and the small side will be positive. So if we sum 7 positive things, we surely get something that's bigger than 0. On the other hand, we can consider for each single vertex how much that vertex or that vertice's weight contributes to this sum. So let's look at the weight of 1, 2, 3. Now, if we assign some weight to the vertex 1, 2, 3, then this vertex appears on the big side of exactly 3 maximal separations, A1, B1, A2, B2, and A3, B3. So the weight that we assigned to 1, 2, 3 will feature with a positive sign here exactly 3 times. Now, for the other 4 maximal separations, this vertex 1, 2, 3 will be on their small side. So for the other 4 separations, the weight here will contribute to the minus weight of the small side. So no matter which non-negative weight we choose to assign to this vertex 1, 2, 3, it will have a net negative effect on the sum. And that's true for each vertex in our vertex set. So this sum, which we know to be positive, is in fact very negative. So this shows that this hypergraph, or this edge tangle in the hypergraph, really cannot have a weighted decider. Okay, and that's already the material that I've prepared for today. So thank you. That was much faster than when I tested this.
Thank you. That is a really nice proof. So we don't usually do applause, but I want to try and get that started in the seminar series. So let me ask everyone to unmute themselves.
Very nice.
All right, let's give Jakob a round of applause. So are there any questions? You can just go ahead and speak out, or I can, or you can type it in chat and I'll say it out loud.
So I had a question about the weight functions. Are they arbitrary?
So what do you mean by arbitrary here?
So if I have an arbitrary weighting of the vertices of a graph, will that give me a K-tangle by defining the big side of every separation to be the side of greater weight?
So you mean a sort of opposite of this question?
Yeah, I'm asking which positive functions on the vertex set arise as the weighting functions of K-tangle?
I don't think that a clear answer to that is known.
Yeah, that was the feeling I was getting, that you can't just say, okay, this vertex will give me 5 points and that one will give me 3 points.
I think if you just arbitrarily distribute weights among the vertices, you're not guaranteed that choosing the big side will obey the second tangle property. You might run into cases where 3 small sides do happen to cover the graph, but barely.
So that would be something interesting to see if you can. I mean, the theorem as it stands does not give you a recognition strategy for K-tangle.
No. So this is only one way. This is not a characterization of these weight functions. And I think we have some computer-generated examples where at least distributing uniform weights does not yield a tangle.
Thank you.
I have a couple of related questions. So the main question I'm interested in is whether you can make the weights polynomially bounded.
I don't think you can, at least not the way that we state this here. So what I didn't really go into detail here is that we want this weight function to be integer valued. But the Forkash lemma is going to give you real valued vectors.
So rational.
Excuse me?
Rational.
Yeah, I think you can sometimes guarantee that they're going to be rational, but there's always going to be a step where you have to turn those rational weights into integers. And I don't think we have any way to get a bound on how much worse or how much bigger that's going to make the weights.
Yeah.
So we did investigate whether we could give any bounds on the size of the weights for at least a couple of days, and we did not find a way of doing that.
Yeah, it'd be really nice if we could get something that would be good.
Yeah, true. So polynomial bounds would be, at least to me, slightly surprising. Because these tangles feel like a somewhat complex thing, and I think there are at least some NP complete problems you can phrase as existence problems of, well, at least of tree decompositions, and then sometimes also of tangles. So if you could have polynomial weight functions for tangles, that would be a bit surprising for those things.
I know sort of results of that kind for tree decompositions. I don't know any which would really preclude the notion of a sort of that tangle should be easy to certify. I don't know anything that would make that. Do you know anything concrete there that would?
No, I don't think
polynomially certify a tangle. Do you know a concrete result that would say that this would be unlikely, or I mean that would?
No, I don't think that there is a concrete NP complete thing about the existence of tangles. But since they are sort of dual to tree decompositions, it always felt that there should be. But I don't have one, no.
The things I know with tree decompositions are also wouldn't be just for graphs. I don't know. I mean, I know. Yeah, so maybe. Yeah, I don't see a good reason why there shouldn't be a good certificate anyway. But, I'm kind of more of the belief that there probably should be a nice polynomial certificate myself, but.
Okay.
And in a stronger sense, what I would really like is a certificate that also enables you to compute the connectivity of a set into the tangle. Right? You've got this matroid associated with the tangle. And to actually use the tangle, you need to be able to compute connectivities into the tangle. So it's also not clear to me that if I have a weight function, whether I can actually use the tangle. Like I can, if you give me a separation, I can tell you which is the big side. But if I have a set of vertices, I can't tell you whether it's highly connected into the tangle, which is usually what you need when you want to be able to actually do something with a tangle, right? You want to know whether this is actually a highly connected set from the point of view of the tangle. So is that set of vertices independent in the associated tangle matroid?
Yeah, so these weight functions only give you an oracle for the actual separations in the tangle, not for any vertex set, as you say.
Thought about that problem at all?
I did not really know.
Get a notion of, so to get some sort of certificate that enables you to actually compute for the tangle.
So I have to admit that despite this being the matroid union seminar, I'm actually not that well versed on matroids. So there are probably people in our research group that are more qualified to look at a problem like that.
So the matroid I'm talking about is just you just have so basically I give you a set of vertices and I want to know what's the lowest order of small side that contains it. So that's the connectivity of a set of vertices into a tangle, which is sort of a natural notion, and it just turns out to be the rank function of a matroid. So that's what I would be interested in if I had some way of showing somebody a tangle which enables them to compute that. Then you could actually do the kinds of computations one does with tangles. Like if you actually wanted to do anything with a tangle in a graph, that's what you would want access to.
So there is a fairly large paper by Groh and Schweitzer on what you can and can't do with these connectivity functions and tangles in graphs. But it's not fresh enough in my mind to make any definitive statement of what they did or did not do in that paper.
Okay.
Maybe we can discuss that more later because I've got another announcement in this off. So let me go ahead and stop.